In this video, we're going to show that least squares estimators are unbiased. So we recall that in the scenario where you have these random variables, say capital Y1, capital Y1 through capital Yn, and you have this data set x1 for xn, okay, and you define, say, yi to be alpha plus beta little x1 plus capital Ui, where these ui's are independent, so u1 through un, these are independent random variables with the expected value 0 and variance sigma squared, that are least squares estimators of alpha and beta are alpha hat, which is defined to be the average of the yi's minus beta hat times the sum of the xi, times the mean of the xi's, where beta hat is equal to n times the sum of the xi yi minus the sum of the xi's times the sum of the yi's divided by n times the sum of the xi squares minus the sum of the xi squared. So these are random variables, right? Your yi's are random variables. So these are random variables. And we say that random variables are unbiased. Random variables that are estimators of alpha and beta are unbiased if the expected value of those random variables are equal to alpha and beta respectively. So the claim is that the expectation of the random variable alpha hat is alpha, and the expectation of the random variable beta hat is equal to beta. Okay. Okay. Where beta is well, you should get beta. Oh, see, it's complicated because the notation is weird because I'm using alpha hat and beta hat as random variables and then alpha and beta as the actual constants, right, that are from the least squares line. Okay. So first we'll show that the expected value of beta hat is equal to beta. Well, we have, so beta is equal to the thing above, and then when we take the expectation, we can use the linearity of expectation, so the denominator is just a constant, right? And you have the yi's showing up where they show up, and then you can apply the linearity of expectation to get that this expectation is n times the sum of xi times the expectation of yi minus the sum of the xi's times the sum of the expectations of the yi's, divided by n times the sum of the xi squared minus the sum of the xi squared. Well, the expectation of yi is equal to alpha plus beta times xi. So that's because when you take the expectation of the y here, you get alpha plus beta times the expectation of xi, this is xi, plus the expectation of ui, but ui has expectation 0. So you get that, and so when you plug that in here, when you plug this in here and plug it in there, you are going to get n times the sum of xi times alpha plus beta xi minus the sum of xi times n alpha plus beta times the sum of xi. Right? Because you're summing alpha n times, and then you have beta times x1 plus beta times x2 all the way to beta times xn, so it's just beta times the sum of the xi's. And then the denominator stays the same. Okay, now we can distribute the sum across. So you're going to get n times alpha times the sum of xi plus n beta times the sum of the xi squared. And then minus n alpha times the sum of the xi's minus beta times the sum of the xi's in parentheses squared, with the same denominator. And now what's going to happen is this n alpha sum of xi's will cancel in the top, and so you're going to get n times beta times the sum of the xi squared minus beta times the sum of the xi's in parentheses squared. Well, now I think we can see what to do now. You just factor the beta out from the top, and then this other factor is going to cancel with the bottom, and you're just going to get beta. So that shows the expectation of beta hat is equal to beta, and that completes the calculation. Now from that, we can deduce that the expectation of alpha hat is equal to alpha. So let's see why. Because the expectation of alpha hat, well, that's going to be the expectation. So alpha hat was yn bar minus beta times xn bar. So here your random variable is yn bar, right? So this is the expectation of yn bar minus xn bar. Oh, we have beta hat is also a random variable. So times the expectation of beta hat, that's just beta, so expectation of the yn bar minus xn bar times beta, right? That's what we just calculated. The expectation of beta hat is equal to beta. Well, the expectation of the average, we again apply the linearity and get that as just 1 over n times expectation of y1 plus dot 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 plus expectation of yn minus, xn bar times beta. And we know that expectation of yi is equal to alpha plus beta x1 or xi. And so we just get alpha plus beta x1 plus dot 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 plus alpha plus beta xn. Probably could have simplified this using the summation notation, but whatever, you're going to get 1 over n times n alpha plus beta times the sum of the xi's minus xn bar times beta. So that's going to be alpha plus beta times the summation xi's divided by n minus xn bar beta. And now these are going to cancel, and you're going to be left with alpha. So that proves that the expectation of alpha hat is equal to alpha, which means that alpha hat is an unbiased estimator of alpha. And so that completes the proof that alpha hat and beta hat are unbiased, that these least squares estimators of alpha and beta are unbiased.